Good morning. Today we're starting chapter 10, and this chapter is gonna be about speed, travel time, as well as delay studies. So the presentation outline for this chapter, we're gonna start talking about a little bit of introduction on these studies that we're gonna talk about, and then what are the other studies that we will be conducting here and learning. The first one is the spot speed study, and then the travel speed or travel time studies, and the third one would be the intersection delay study. So as an introduction, we all know that speed, travel time, as well as delay are all related measures that commonly used as an indicator of the performance for traffic facilities. For example, if the speed at certain facility is high, let's say 65 or 75 miles per hour, versus another facility that has 40 miles per hour, then this is going to give an indication that the facility that has a speed of 65 is much better than the one that has 45 miles per hour. Same thing for travel time. If I have a facility that's gonna allow me to travel from point A to point B in 40 minutes versus going from point A to B through another route in 50 minutes, then you would take the first route, because again, this is gonna give you an indication of how good is the traffic and the transportation facility of the first route compared to the second. Same thing for delay. If the delay is higher, that means it's not a good thing to have, and therefore you would look for a better transportation facilities with the minimum amount of delay. So the question, as I said before, is how long does it take really to get from point A to point B? All the drivers have the obvious desire to complete this trip or any trip and the minimum time consistent with safety. So we're not jeopardizing the safety, but we want to have the shortest route in terms of shortest travel time with the highest speed while maintaining the safety. So the average travel speed is actually used as a measure of effectiveness for arterials and for two-lane rural highways as well. When it comes to the delay, control delay is simply a measure of the effectiveness of a signalized and stop controlled intersections. Those are the two major spots where we have signals or we have stopped control to see the effectiveness of a delay. Freeways also use density as a primary measure of effectiveness. So if I have lots of density in a freeway, that's not a good thing. If the density is lower, that's a good thing to have. And also speed. Speed is a very important component of the evaluation of freeway system operation. So the speed is higher, as I said, then that's a good thing to know about certain facility compared to a lower speed at a different facility. So when it comes to speed measurements are often taken at certain point or a very short segment of a roadway under conditions of free flow. And the major goal that you have to keep in mind while doing a speed study is that you need to determine the speed that drivers select, which basically is going to be unaffected by the existence of any congestion. So once you have a congestion, that would not be a good candidate to do a speed study. The speed study is also used to determine general speed trends in order to help to determine reasonable speed limits. So even the speed limits, as well as assessing safety issues, we have to do a speed study in order to address those issues. Also, speed studies are referred to as a spot speed study. The reason why I'm saying spot speeds is because they are measured in terms of travel times over a short measured distance. Typically, it's much less than 1,000 feet. When it comes to travel time as well as delays, it's the other way around. Travel time must be measured over a distance. So typically it's measured and it's made over a significant length of the facility, and also the delay, which is part of the travel time, is particularly identifiable and unusually annoying to the motorists because they are expecting that much of delay. So what are the types of delays at any intersection? So we have here four different types of delays. The very first one is the stopped time delay. Stopped time delay is simply the time a vehicle would spend stopped waiting for a process through a signalized or stop controlled intersection. So this is again, it has to be there, and that stop time, it's gonna happen while waiting for a signalized intersection. So it's typically during a red time. If it's a red time, you're just at speed equal to 0, and this what we call as a stopped time delay. Approach delay is actually the delay during the deceleration or an acceleration from a stop to a stop time delay. So if you are now, let's say if you are driving at 45 miles per hour and you are approaching a signal, and all of a sudden it's turning red, and now you're gonna push on the brake to decelerate. So it's gonna take you some time from 45 miles per hour till 0. Once you reach 0, this is a stop time delay. But from the time that takes you from pushing on the brake and lowering your speed from 45 miles per hour to 0 miles per hour, this would be what we call the approach delay. It also happens after the green light starts. So once the green light starts, you are gonna push into the fuel, start accelerating, and it's gonna take you some time to reach the speed limit. Let's say it's gonna take you from 0 miles per hour until you get back to 45 miles per hour, just a few seconds. This is what we call approach delay. The third one is the time in queue delay. Time in queue delay is simply the time between a vehicle joining the end of the queue at a signalized or a stop controlled intersection and the time it crosses the stop line to proceed through the intersection. So this is again time while you are in queue. Now you are waiting and waiting between a vehicle joining, as I said, between a vehicle joining the end of the queue at a signalized section and the time it crosses the stop sign. So again, there's a difference between this one and the stop time delay. Now the control delay is basically the total delay at an intersection caused by a control device, either by a signal or stop sign. And this is going to be including both time in queue delay plus delays due to acceleration and deceleration. So control delay is going to be simply the time in queue delay plus the approach delay. So let's start with the spot speed studies. Spot speed studies are typically conducted to document the distribution of a vehicle speeds as they pass a short segment of that roadway. There are several key characteristics that we need to obtain while doing the spot speed study distribution. The very first one is the average or time mean speed. We need to get the standard deviation speed. We need to get the 85th percentile speed, as well as the median, all the way to what's the pace speed. So the very first one is simply, again, this is the average time speed, which is an average speed of all the vehicles passing through the study location during the period of the study. So for example, if you go for half an hour, you counted 100 vehicles, you sum up all the speeds of those 100 vehicles over 100, and that will be the average or time mean speed. Then you need to get the standard deviation, which we all know, the 85th percentile speed. What is the 85th percentile speed? It's simply the speed below which 85 of the vehicles are traveling. So you need to do, again, we're going to go through a calculation to show you how to get it, but basically we're interested now to see, besides the average speed, 85% of the vehicles are less than that speed. That would be the 85th percentile. The median speed is also important. The median speed is the speed that equally divides the distribution of spot speeds. 50% of observed speed are higher than the median, and 50% of the observed speed are lower than the median. So it's exactly in the middle. The pace is basically, it's a segment. It's a 10 mile per hour increment or a segment in speeds that encompasses or that includes the highest proportion of the observed speeds. What we're saying here is what's the majority of vehicles are traveling at what speed. So we need to obtain, let's say, if I am in the loop and the speed limit is 55, and if I tell you that the pace is 45 to 55, that means the majority, the highest proportion of the observed speed was between 45 and 55 miles per hour. So why do we need the spot speed studies? So there are several usages for having spot speed data. The very first one is really we need to establish the effectiveness of a new or existing speed limit. Sometimes if the speed limit, there are some complaints about it. If it's too high, maybe it's unsafe in some places, for example as school zones, or if it's too low at some other places, it's too safe and everyone is saying it should be higher. Then we need to do a spot speed study over there to know exactly if we are really can increase or decrease the posted speed limit. It can be also for new structures, for a new transportation facility, a new road. If we don't know it, we typically, before we post it, we either do it in a nearby location with similar characteristics, or we would delay the postage of the limit speed for some time until we have some collection of the data to know exactly what would be the speed limit. So we would start from a very default value based on the AASHTO or the MUTCD standards, and then until we do our own spot study for that new structure. We also use it to determine appropriate speed limit for our applications. Third is also we can establish speed trends at local, state, and national levels. So that's also very important to know that the speed trends and our people are increasing their speeds more than the speed limit, or is it less, from the local, state, and the national perspective. We also use it as a way of determining appropriate sight distance, which is we use it for geometric design. So if you know the speed, if the speed is high, that means you would need more sight distance, and therefore the curvature of the road is going to be much different than if the speed is much lower, where the driver has much longer time to react, and therefore we don't need that long of a sight distance. We also need spot speed studies for designing the timing of yellow as well as all red intervals for traffic signals, as well as we can use the spot study in investigation of any high accident locations. Whenever we have a location or an intersection that has repeatedly a bad history of accidents at this location, then we have to do a spot speed study to see if the speed is really the true reason behind having that high percentage of traffic or of traffic accidents at that location. Here we can see a form that we typically use for spot speed studies, and for the first two columns here you would see we need to have a speed group. What do I mean by speed group is, before going to the field, you are interested to know how many vehicles are traveling at certain segments of that speed. So, and typically we set it at 1 to 2 miles, not more than 5 miles. So, for example, here we're having speed limit, the lower is 30 and the upper limit is 32. So I'll be interested to see if how many cars and trucks are traveling from 30 to 32, and then from 32 to 34, 34 to 36, and so on until you reach 68 to 70, simply because you want to have a good estimate of how many cars per certain segment of the speed, because eventually what we are going to see, we are going to develop a normal distribution to develop the statistical analysis, which is including average, standard deviation, the 85th percentile, as well as the pace. Also, it is recommended to collect from somewhere between 15 to 20 speeds for each designed and for each specified speed group. At least the middle range here, we need to have at least 15 to 20 speeds at each one of these groups. For example, here you could see we're having 46, 33, 21, but of course when you hit the lower ends of the speed or the higher ends of the speed, you will not be able to see that many cars are exceeding the speed limit in this case, or way lower than the speed limit in this case. Now we're going to the analysis part of the speed study. So the very first two columns, as we discussed before, those are the lower limit and the upper limit. And typically when it comes to analysis, we pick the middle speed as the midpoint value within the speed group. So, and this is here what I put here, because eventually you need to plot a curve, a bell-shaped curve like the normal distribution, something like this, and therefore you need to have certain point. You cannot have a lower or upper limit. So typically we pick the middle point. So if it's 32 to 34, we pick 33. For example, here 62 to 64, we pick the midpoint, which is 63. Then this is what you observe in the field. This is really here how many cars. For example, we've got 7 cars that they were traveling somewhere between 38 and 40 miles per hour, while the highest amount of cars, they were at speeds from 48 to 50. So from 48 miles per hour to 50, we've got 62 vehicles at that speed range. So what you need to do again to sum up all the numbers to get the value here, the total number of observed cars, and then now you need to start your calculation. So all what you have to get from the field is how many cars at certain speeds, and then you need to get this column here, which is the percentage frequent in group. So basically it's gonna be the number of observed vehicles at any certain speed over the total times 100%. For example, again, the 62, which is the highest frequency, 62 over 283 times 100 is gonna give you 21.9%. Something to double check here, all the numbers here, all the frequencies has to sum up at the end to be 100. So that's the first thing that you need to do in calculation. Then you also need to get the cumulative frequency, because this is the cumulative frequency also is going to be used in the statistical analysis that we will be showing in a minute. So how to get the cumulative frequency? The very first one is always 0, then, or whatever the first value, and then the second one now we're going to accumulate is going to be 0 plus 1.8, which is going to give us 1.8. And then 3.5, how we get the 3.5? It's 1.8 plus 1.8, but here again there is some rounding, that's why it's not exactly 3.6. And then 3.5 plus 2.5, that's going to give us 6%. 6% plus 4.6, that's going to give us 10.6, all the way until you reach the very last number here, the cumulative. Since it's cumulative, it has to end up with 100. Next, we're in this column here, we are doing n times s. What is n times s? It's the speed times the observed frequency in that group. So for example, 33 times 0, that's 0. 35 times 5, that's 175, all the way to the highest range, like what we saw here. It was the middle speed, which is 49 times 62, and that will give us 3,800. I'll show you in a second why we do need this. So, but again, this is n times s, and we need to get the summation of this number as well. Same thing also, the last column here, now we're going to do n s squared. N s squared. So it's going to be the observation times the speed squared. As you can see here, there are some notations here for the percent frequency in group. We have here all percent computed to 2 decimal places are rounded to 1. This is the one that may cause the error in cumulative percent due to rounding. So again, just keep that in mind. Also, the double stars here is the computation rounded to the nearest whole number. So typically we do not carry fractions in this calculation. So in a summary, you need to have lower speed and upper speed. You would pick the middle speed as the representative value, and then this is what you observe in the field, get the summation, and then you would be interested to know the percent frequency for each one of those speed ranges, and they have to sum up to 100, and then you get the cumulative. Here you would do the speed times the middle speed times the observed frequency, and here the speed squared times the frequency. Now, based on the information that we collected from the previous table, we can generate two different frequency distribution. The very first one is the frequency distribution curve, as well as the cumulative frequency distribution curve. So as you can see, once we develop these two, we will be able to put on the figure what's the mode speed, what's the pace, what's the median speed, and we will be talking about those details in the next slides. So first, based on the analysis of a spot speed study, we have two distributions, as we said, frequency and cumulative distribution curves. The two frequencies are plotted versus different speeds. In fact, as I mentioned, the middle speed is used for the frequency distribution curve. When it comes to cumulative frequency distribution curve results, those are ones that are very useful plot for speed versus the percent of vehicles traveling at or below the designated speed. In fact, the upper speed limit of the speed group is used as the plotting point. So here I need to make sure that you got the difference. When it comes to the frequency distribution curve, we are using the middle speed as the x-axis. When it comes to the cumulative frequency distribution, which is again very useful, but here we use the upper limit speed group as the plotting point. Common descriptive statistics that we need to get out of these two curves. First thing is the two major groups or two major families of statistics. The first one is the central tendency, and the second is the dispersion. The central tendency is basically measurements that describe the measures that describe the approximate middle or center of the distribution. So this can include the mean, the median, the modal speed, as well as the pace. When it comes to the dispersion, those are measures that describe the extent to what data spread around the center of distribution. For example, we would be interested to get the 85th percentile, which is again what's the speed below which 85% of drivers are traveling. How about the 15th percentile? Because also I'm not just interested to know what's the maximum speed limit or what's the maximum speed limit that 85% of the travelers are following. I'm also want to see what are the lower speed drivers are experiencing. So that would be the 15th percentile. So some of the common descriptive statistics. First of all, we get the mean speed. So the mean speed is simply what you need to do to get the average or the mean speed is Ni in this equation is the frequency of observation and any speed group times Si, which is the middle speed of that speed group, over the total sample size. So simply, as I mentioned in the table, is going to be you would multiply the speed times n over the total number of cars that were observed. And that's why, if you recall, in the last two columns we got ns and ns squared. So ns we would use it for the average speed, and ns squared we're going to be using it in the standard deviation in the next slide. So for now, if you go back to the results, you are going to see that the summation of the second column from the right was 13,613, and if you divide this by the number of observed cars, which is 283, we will get an average speed of 48.1 miles per hour. Another common descriptive statistics number that we need to obtain is the median speed. Median speed is simply a positional value which is really not affected by the absolute value of the extreme observations. For example, if I have three speeds that they were observed at certain location, 30 miles per hour, 50 miles per hour, and 40 miles per hour. as you could see here. The average is 40 miles per hour, but their median is also 40 miles per hour, because the median is the number in between. So if you put them in a arranged order, you would eliminate one from the small or from the low side and one from the high side until you have the middle one, and that would be the median speed. So here it happens to be that the average is exactly as the median speed, simply because it equally divides the distribution, with one speed higher than 40 and one speed lower than 40. How about if you go to another location and you have three other speeds, which is 30, 40, and 70? The average speed is 46.7 miles per hour, while the median speed is 40 miles per hour, which is different than the previous example. With one speed higher and one speed lower than the observation, now we see that there is a huge difference between the median, which is 40, all the way to the average, which is 46.7. So the question is, how can we get the median? You can get the median by two ways. One, by arranging all the speeds, observed speeds, including repetitions. For example, you can start with, and let's say I've got 30, I've got 32, I've got another 32, I've got 40, and I've got 50. So I need to put all the speeds, including repetitions, in a descending order. Then I'm gonna remove the lowest one and remove the highest one. Do the same thing, remove the second lowest one, the second highest one, and the one in the middle that's gonna stay there. This will be the median speed. Another way, which is an easier way of doing it, is you can use the cumulative frequency distribution curve. If you go to the cumulative frequency distribution curve, it would be at the 50% cumulative. So if you draw the curve like what we had before, and start almost with a 0, and it reach up to 100, like this is here 100, the way to get the median speed is to catch the speed at 50, go all the way to here and go down, and that would be your P50, which is the median speed. Another common descriptive statistics is the pace. So the pace is, as I said before, is the 10 mile per hour increment in speed in which the highest percentage of drivers are going to be observed. It can be easily found graphically using the frequency distribution factor. The frequency distribution factor, not the cumulative one. The solution basically recognizes that the area under the frequency distribution curve between any two speeds approximates the percentage of vehicles traveling between these two speeds. So the way to get it is, you would have a 10 mile per hour template is scaled on a horizontal axis, and now you need to keeping this template horizontal, and you would place it at the end on the lower left side of the curve and move it slowly along the curve. When the right side of the template intersects the right side of the curve, then the pace has been located. For example, if you go back to your curve, you would see by following this procedure that the 10 mile increment is between 43.5 to 53.5 miles per hour. Another common descriptive statistic that we are interested to get is the modal speed. Modal speed is defined as the single value of speed that is most likely to occur. So we need to look into what's the most frequent speed that happened during the observation. And for this case, we had the modal speed was 42.9 miles per hour. This one that they have the highest frequency. The way to get it, you can also get it graphically by drawing a vertical line from the peak of the curve. So if you have a curve like this, the frequency distribution curve, and you would just go to the peak, go all the way down, and that would be the modal speed, the most frequent speed observed during the speed study. Another common descriptive statistic besides the mean, modal, and median speed is now the standard deviation, which is really a measure of dispersion of the data. So because discrete values of speed are not recorded, we can use actually this equation here, which is Ni, this is the number of vehicles at that range, and S the speed minus the average over N minus 1, this is the total number of vehicles minus 1. This is here the general equation that we get from math, but this is here simply the one that is applicable in our case. And to be even for more convenient, you can go all the way to the simplest form, which is here, and that's why you see from the table that we discussed early on that we need this value here, which is the N, what's the frequency of the car at certain speed, times that speed squared, minus N, which is the total number of cars, times the average speed squared over N minus 1. So for our case, if you do the calculation, which was the major thing was really this number here, which was the last column, the summation of the last column, which is 661,691, minus the number of observed cars, which is 283, times the average squared over N minus 1, which is 183 minus 1, is going to tell you that the standard deviation was 4.96 miles per hour. The last two common descriptive statistics that we are interested in any spot speed study are the 85th and the 15th percentile speeds. Those two percentile speeds typically give a general description of the high and low speeds observed by most of the reasonable drivers. We're not talking about crazy drivers that they're gonna drive 100 miles per hour on 75 miles per hour limit, or 10 miles per hour if it's 50 miles per hour speed limit. But it's 85th to 15th percentile. Those are generally thought that the upper and lower 15% of the distribution would really represent speeds that either too fast or too slow for existing conditions. You can find these two numbers graphically from the cumulative frequency distribution curve. If I would draw it here, and now this is the cumulative, so it starts from 0 and go all the way to 100. Basically, you need to enter on the vertical axis 85 and 15%, so 15% is going to be here. Draw a vertical line, and that would be the P15, or the 15th percentile speed. And now we can do the same thing at the 85th percentile. Draw a horizontal line and then vertically, and that would be the speed with the 85th percentile speed. In this case, we have the P85. It happened to be 52.7. That means 85% of the drivers drive less than 52.7 miles per hour, and P15 is 43.7. That means only 15% of drivers drive less than 43.7 miles per hour at that facility. With this, we finish the spot speed studies, which is for this lesson, and next time in the class we will be talking about the travel as well as delay studies. Thank you.